Now I think we're ready to talk about the EM algorithm for a hidden Markov model. And we wanted to estimate the parameters theta that maximize the log likelihood, which is the marginal likelihood involving only the observation x. And how we compute the marginal likelihood of x is equal to the summation of x, the joint of x and the latent states z. So it is difficult to optimize this likelihood because of this summation inside the log. And this is a perfect example for us to apply an EM algorithm. So I'm going to work with the log likelihood for the complete data z and x. And here we will purposely write z in an uppercase just to remind us that z is latent and we do not observe. And then the joint likelihood of z and x can be written pretty easily. We first use W to generate the first z1, and then we can sequentially use the transition probability to generate the future z's. And then given z, we can use the emission probability b to generate x. And once we take log, and the joint likelihood becomes those summations. Here, the summation is from from 1 to n-1 because we already generate z1, so there are only n-1 z's. We need to compute the corresponding probabilities. In the EM algorithm, we have the first step is the E step, and we have to compute what is the distribution of z given x and some initial value of theta. Now remember here our z actually is in a bold phase, so it's z1 through zn. And each of the zi can take m and z different values. Now without loss of generality, let's assume our mz is equal to 3. Okay, so there are 3 latent states. This distribution of p of z1 through zn given the data x1 through xn and some initial parameter theta 0. This seems difficult to keep track because it is apparently those z's won't be independent, so we have to keep track of a joint distribution of n random variables. But it turns out if you look at the log likelihood, seems what's relevant would be just the marginal distribution of some of the z's, and also only the joint distribution for a pair of z's. So we're going to define gamma Tij. You can think about this gamma Tij as a matrix. Again, if we assume m sub z is 3, so there are 3 latent states. So you can think about each of this gamma Tij as a 3 by 3 matrix. And every entry, the 9 entries would be the probability for zt takes one value and zt plus 1 takes another value. So that if you sum the 9 numbers together, they should be equal to 1. And once we have this table, how many tables we have? We have actually n-1 such tables. Okay. Once we have this table, and we don't even need to keep track of the marginal distribution of each of the zt, because for those tables, the row represents zt, and the column represents zt plus 1. So if we do row sum of this gamma matrix, we basically get the marginal probability of zt. Okay, so once we have this gammas, and then we can evaluate the expectation of the log of the joint likelihood. This is basically the g function in the EM algorithm. So the expectation calculation is pretty straightforward. We want to evaluate the expectation of a sum that's equal to sum of those individual expectations. Because all the zj's takes discrete values, so all the expectation becomes summation. So the expectation of z1 is a summation over different value of z1, and then the expectation of a pair of random variables zt and zt plus 1 becomes the summation over both I and j, a double summation over ij. and then the expectation over zt and becomes a summation I from 1 to mz. Okay, so we get this g function. Now for this equality, we basically just rearrange and some of the summations, like we switch the order of these two when we get this one, and we switch the order of these two and we got this one. And then we continue the calculation. The first line is basically a copy of what we had on the previous slide. And then we're going to continue to reorganize the summations. The first summation stay the same. Now for the second summation, note this is a summation over t, and t only appear here. So we're going to rewrite this summation as a number, which is I called gamma subscript plus, meaning just sum over the subscript t. So this is a number. And then we also spell out the double summation and I and j. And then let's here this summation is over t. T is from 1 to n. Now remember xt would only take mx different values. So when we sum this summation over t from 1 to n, which are all the data sequence, we can break that summation as follows. We first summation over L from 1 to mx, which are the different values of xt. And then we sum over all the time points where xt is equal to L. And then we can add a parenthesis because this summation is over t. It has nothing to do with other terms. So now this star, so this 3 summation is the g function in the EM algorithm. What we're going to do next is going to find a value of theta, which actually is the w, a, and b, to maximize this g function. At the m step, you'll see that we're going to repeatedly use the following result, which we have shown before, and consider the following function of w1 until wm, which is an a1 log and w1 plus a2 log w2 all the way to am log and wm. Here all the aj's are non-negative numbers. They are not necessarily integers. It could be 1.2. And the parameters here and w1 through wm is a probability vector, meaning the wj's must take value between 0 and 1, and sum together is 1. And we have shown before that the maximum of this function jw as a function of w is achieved by setting this probability wj proportional to aj. So wj is equal to aj divided by the sum of those aj primes. Now we can start updating those parameters. First is w. W is the discrete distribution over z1. And the only term involving w would be this one. Now we can use our result, and we know that we should set our wi to be proportional to gamma 1I. But we don't need the normalization step here because gamma 1I, which is the probability of z1 equal to I using the initial parameter value theta 0 conditioning on the data x. So the gamma 1I and the summation over I is already 1, so we don't need to have this normalizing step. So the optimal wi is equal to this. And next, we're going to update the transition probability matrix A. Remember, each row of A is a probability vector because it is the probability of transition from I to the other MZs and latent states, including the ith latent state. So we can do the update of A for each row. Let's fix, if we fix I, or for any given I, let's look at this term. So because for any given I, this over j is a probability vector, we can use our result here. So we know the optimal choice for aij would be proportional to this number. So that's our solution. So the optimal a's and aij would be equal to this. And if you spell out what is the definition of gamma and subscript plus, and we have this expression. And the last step is update B, the emission and probability matrix. Again, remember each row of B is a probability vector. It denotes a distribution. Given the current state, latent state is I. What is the distribution of over the m sub x different x values? Now, if we go back to look at the expression involving B, for any given I, and we have what's relevant is in this summation inside the bracket, and we can use our result again, and we know that we need to set our BIL proportional to this number. So that's the solution. And here, so we just described the EM algorithm for hidden Markov model. We're going to start with some initial value of theta. Then we can compute the gamma matrix. Then we have formula to update W, A, and B. And then once we get the new parameters, we can go back to recalculate this gamma matrix and then update W, A, and B again until convergence. And here I want to point out that sometimes it is not really necessary to update W. Why is that? W is the distribution for Z1. Distribution for Z1. Okay, Z1 is a discrete random variable taking M, Z, and different values. And consider the following example. There is a loaded die, and you wanted to know, you want to estimate the probability of seeing the 6 outcomes if somebody threw the die. So there are 6 probabilities you need to estimate. Now, if you only observe one observation, like one result of this die, suppose is 2, then it doesn't make any sense to get a reasonable good estimate of the probability over 6 possible outcomes because you only see one observation. And that's sort of this the case for Z1, because in the hidden Markov model, we have only observation X1 is related to Z1, and Z1 is sort of related to Z2, but Z2 is also latent, so the information so overall the information for Z1 is really limited. So it's okay not to update W, or in other words, just use whatever initial value, for example, equal uniform distribution over the MZ different values as a starting value for W, and just use that W and without updating it in the EM step. And that's what you will ask to do when you implement for your coding assignment 3, because that's what the R package HMM is doing. Well, how to compute this gamma values? And it is by definition is equal to the conditional the probability of ZT equal to I and ZT plus 1 equal to J, given the data x1 through xn. So this is actually given all the data x1 to n, and also our parameter value is theta. As I mentioned before, those gammas, you can view them as a matrix. For example, if we assume our number of latent states is 3, then the gamma, this basically can be viewed as a 3 by 3 table, and we just need to compute the 9 numbers. Now, it is actually sufficient to compute just a joint, because you can compute the joint for all the 9 values, 9 pairs of values of I and J, and then you just divide it by the sum of the 9 values. You get the conditional probability. Now, how to compute the joint? It is a joint of the of x1 all the way to xn, and also 2 latent states at t and t plus 1. And this is a graphical structure of this n plus 2 variables, and you're going to find out, well, this part is what the so-called forward probability, and we computed before. And then this, we know how to compute the forward. And this is a transition probability A. And then this is the emission probability and computed through B. And then this part is basically the beta, the backward probability. The product of the 4 terms is from this chain rule, and you can go back to check. We start with the marginal of x1 to t and zt, and zt plus 1 given all the previous, but it will only depend on zt. And the xt plus 1 given all the previous, but it will only depend on zt plus 1. And then the remaining of t plus 1 to n given all the previous, it will only depend on zt plus 1. And so in your EM algorithm, and inside your EM algorithm, for each iteration, you have some current value of theta. Then you have to first update your forward, calculate all your forward probabilities, calculate all your backward probabilities, and then use the formula here to compute all your gamma, and then you can update your parameters. And then you go through the loop again.